Dear students, in this video we will discuss about crystal field theory in coordination compounds. The crystal field theory was developed by Bethe and modified by Van Vleck in 1935 to explain the bonding and properties of coordination complexes. And it was proved to be more successful in explaining the properties of coordination complexes than the valence bond theory that we saw in the previous class. According to crystal field theory, the bonding between a central metal ion and its ligands arises from purely electrostatic interactions. We know that a metal ion is positively charged. The ligands will be negatively charged or neutral molecules. So there will be an electrostatic interaction between the oppositely charged metal ions and ligands. If the ligand is an anion, the attraction towards the metal cation is as that between any oppositely charged particles. And if the ligand is a neutral molecule like ammonia or water molecule, the negative end of the dipole is attracted towards the central positive ion. In crystal field theory, the bonding between the metal ion and the ligands is assumed to be ionic, and it arises from the electrostatic attraction between the metal ion and the ligands. Here, the metal ion and the ligands are considered as point charges. We saw that there is an attractive interaction between the metal ion and the ligands. In a similar way, there is also a repulsive interaction between the d electrons present on the metal ion and the ligands. The 5 d orbitals are degenerate, meaning they are having the same energy. According to CFT, the approach of ligands will break the degeneracy of these d orbitals, and the orbitals will split into different levels. This concept forms the basis of crystal field theory. This theory qualitatively describes the strength of the metal ligand bonds. Based on the strength of the metal ligand bonds, the energy of the system is altered. And this may lead to a change in the magnetic properties as well as color. So crystal field theory could successfully explain the magnetism and color exhibited by coordination complexes. Before going to more details about the crystal field theory, let's discuss about the orientation of d orbitals. We know that there are 5 d orbitals. The first one is dxy. In dxy orbital, the lobes lie in between the x and the y axis, as you can see here. Here, the lobes lie in between the x and the y axis means the electron density is oriented in between the x and the y axis. Next is dxz. Here, the lobes lie in between the x and the z axis. In dyz, the lobes lie in between the y and the z axis. Next is dx square minus y square. In this orbital, the lobes lie on the x and the y axis. That is, the electron density is oriented on the x and the y axis. And the last one is dz square. Here there are 2 lobes on the z axis, and there is a donut shaped ring that lies on the xy plane around the other 2 lobes. So these are the 5 d orbitals which remain degenerate in a free metal ion. Now let's see what happens when the ligands approach a metal ion in an octahedral complex. We know that in an octahedral complex, there will be 6 ligands attached to the central metal ion. These 6 ligands approach the metal ion from the 6 corners of the octahedron along the x, y and z axis. In a free metal ion, all the d orbitals are degenerate, or they are having the same energy. Now suppose a hypothetical condition, that is, the metal ion is spherically surrounded by ligands, or they are having a uniformly spread negative charge, and there will be repulsive interaction between the metal d electrons and the negatively charged ligands, and due to this repulsion the energy of the d orbitals will be raised. But since the charge distribution is spherical, or since it is uniform, all the d orbitals will be raised in energy by the same amount. That means they would still remain degenerate. But here we are considering an octahedral field of ligands. As I said earlier, the ligands are approaching from the 6 corners of the octahedron along the x, y and z axis. So among the 5d orbitals, as we have seen earlier, the d orbitals where the electron density is oriented along the axis. That means in dx square y square and dz square, the electron density lies along the axis, so they will be repelled more by the ligands. Why? Because ligands are approaching along the x, y and z axis. So the electrons present in these two orbitals, dx square, y square and dz square, will face more repulsion. At the same time, the electrons residing in the other 3 orbitals like dxy, dxz and dyz, they have electron density oriented in between the x, y and z axis. So they will face lesser repulsion from the ligands. So that means the 5d orbitals, which are originally degenerate, will now be split into different levels depending on the amount of repulsion faced from the ligands. And this splitting of d orbitals in the presence of ligands is known as crystal field splitting. And this is the key point in crystal field theory, or CFT. Now let's see the mode of splitting of d orbitals in octahedral complexes. These 5 boxes represent the 3d orbitals in a free metal ion, which are degenerate in the absence of any ligands. Now when the ligands approach, the d orbitals will face repulsion and will be raised in energy. Now this is a hypothetical condition where the metal ion is spherically surrounded by the ligands, and all the d orbitals will face the same amount of repulsion, and hence they are raised by the same amount of energy. That is, they still remain degenerate. Now what happens when the ligand field is octahedral? As I said earlier, the 2d orbitals dx square minus y square and dz square, whose electron density is oriented along the x, y and z axis, will be repelled more by the ligand. More repulsion means the energy is greater. So these 2 orbitals will be raised in energy, while the electrons in other 3 orbitals, whose electron density is oriented in between the x, y and z axis, will be repelled less by the ligands, and their energy will be lowered. So the 5d orbitals split into 2 different levels. The lower level, consisting of dxy, dxz and dyz, represents the T2g orbitals, and the higher energy levels, dx square minus y square and dz square, representing the Eg levels. So in octahedral complexes, the energy of the dz square and dx square minus y square orbitals increases much more than the energy of the dxy, dxz and dyz orbitals. Just remember, the greater the repulsion, the greater is the increase of energy. So in octahedral complexes, the 5d orbitals split up into 2 sets. One set consisting of 2 orbitals of higher energy, that is the Eg orbitals, and the other set consisting of 3 orbitals of lower energy, that is the T2G orbitals. And the energy difference between the EG and T2G is called crystal field splitting energy, and it is denoted by delta O or delta octahedral, where delta represents the crystal field splitting energy, O represents an octahedral complex. Crystal field splitting energy can also be represented as 10 dQ. So here you can see that the energy of the 3 T2G orbitals are lowered or stabilized by 0.4 delta O, and the energy of the 2 EG orbitals are raised by 0.6 delta O with respect to the hypothetical spherical crystal field or barycenter. Now let's see about crystal field stabilization energy, which is known as CFSE. The energy difference between the distribution of electrons in a particular crystal field and that for all electrons in the hypothetical spherical or uniform field levels is called the crystal field stabilization energy. We know that an electron always prefers to occupy an orbital of lower energy. So consider a D1 metal complex. For D1 species, the electron will occupy one of the lower T2G orbitals. Let it be in dxy. So the crystal field stabilization energy can be calculated as 1 into 0.4 delta O, because there is one electron in the dxy orbital and the T2G orbitals are lowered by 0.4 delta O. So CFSE will be equal to 1 into 0.4 delta O, which is equal to 0.4 delta O, or you can write 4 dQ. So this is the crystal field stabilization energy of the complex. So we can also define the CFSE as the lowering in the energy of the transition metal ion in a given ligand environment due to crystal field effects. Here you can see that the D1 metal complex will be 0.4 delta O more stable than predicted by the pure electrostatic theory. Similarly, for D2 species, the second electron will come to the other available T2G orbital. So CFSE will be 2 into 0.4 delta O, which is equal to 0.8 delta O. Similarly, for D3, the third electron will occupy the remaining T2G orbital, and we can calculate the CFSE as 3 into 0.4 delta O, which is equal to 1.2 delta O. So crystal field stabilization energy is not exactly equal to crystal field splitting energy. Crystal field splitting energy is just the energy difference between the EG and T2G orbitals. But crystal field stabilization energy is the energy difference between the distribution of electrons in a particular crystal field, here in the octahedral crystal field, compared to the electrons in the hypothetical spherical field, or it is also a measure of the stability of a coordination complex. Now let's see how the electrons are distributed and the value of CFSE in D4 to D7 metal ion configurations. In metal ions with 4 to 7 d electrons, there are two possibilities for the arrangement of electrons, and the metal complex can exist as high spin or low spin complexes. While discussing the valence bond theory, we also discussed about stronger and weaker ligands, and we saw that weaker ligands tend to give high spin complexes, whereas stronger ligands tend to give low spin complexes. The pairing of the electrons requires energy, which is known as spin pairing energy. So if the pairing energy is less than the crystal field splitting energy, then the next electron will go into the dxy, dxz or dyz orbitals, that is the lower energy orbitals, due to stability, and that will result in a low spin complex. So if the pairing energy is less than the crystal field splitting energy, the remaining electrons will occupy the lower energy orbitals itself and forms a low spin complex. But if the pairing energy is greater than delta O, that is the crystal field splitting energy, then the next electron will go into the upper energy Eg orbitals, that is the dz square or dx square minus y square orbitals as an unpaired electron, and that will result in a high spin complex. Now let's see how electrons are distributed in the high spin and low spin complexes. First, consider a D4 species. In a high spin complex, that is when the ligands are very weak. Weaker ligands will cause lesser crystal field splitting. So that means this energy gap is less. So the initial 3 electrons will occupy the lower energy orbitals, and the 4th electron may either occupy the upper energy orbital or it may get paired up. But when the ligand is weak, as I said earlier, the energy gap between the lower and the higher energy orbitals is less. So that means the 4th electron can easily jump over to the higher energy d orbital and it occupies one of the Eg orbitals. And this will result in a high spin complex with 4 unpaired electrons. But if the ligands are strong, stronger ligands will cause greater splitting. That is, this energy gap is more. So for the 4th electron, it is difficult to jump over to a higher energy state. The 4th electron will occupy the lower energy orbitals as a paired electron rather than going on to the higher energy orbitals, and this will form a low spin complex. We can calculate the crystal field stabilization energy for the high spin. There are 3 electrons on the lower and 1 electron on the upper. The lower orbitals are less by an amount 0.4 delta O and the upper orbitals are more by an amount 0.6 delta O. So we can calculate the CFSE as 3 into 0.4 delta O minus 1 into 0.6 delta O. So that will be equal to 0.6 delta O. For the low spin, there are 4 electrons on the lower orbitals and no electrons on the higher energy Eg orbitals. So that means 4 into 0.4 delta O, which is equal to 1.6 delta O. Now consider a D5 species. Now when the ligand is weak, we expect a high spin complex. The 3 electrons will occupy the lower 3 orbitals. Now the 4th and the 5th electron will occupy the upper dx square, y square and dz square orbitals, forming a high spin complex with 5 unpaired electrons. And if the ligand is strong, then the last 2 electrons will get paired up in the lower energy orbitals, resulting in a low spin complex. And the CFSE will be for high spin, it is 0 delta O. And for low spin, it is 2 delta O. So in D4 species, for high spin, the electron configuration becomes T2G3 Eg1, and for low spin, it becomes T2G4 Eg0. In D5, T2G3 Eg2 for high spin and T2G5 Eg0 for low spin. Here we can see that in high spin, the crystal field splitting energy is less than the pairing energy, and hence the electron moves on to the higher orbital. Whereas in low spin, the crystal field splitting energy delta O is greater than the pairing energy, and hence electron will get paired up in the lower energy orbitals. Similar will be the case with D5 also. Now next is the distribution of electrons in a D6 complex. We have already seen that in the D5 case, for high spin, all the 5 electrons are unpaired or all the orbitals are singly occupied. Now in a high spin complex, the 6th electron will move on to the lower energy orbital and paired up, whereas in a low spin complex, The splitting energy is more than the pairing energy, and hence the remaining 3 electrons will get paired up in the lower energy orbitals. Similarly, in D7, in a high spin complex, the 7th electron will get paired up here, whereas in a low spin complex, there are no available orbitals in T2G. So the 7th electron will move on to the higher energy orbital. And these are the CFSE values for a D6 high spin and low spin. And these are the CFSE values for D7 high spin and low spin. So in D6, the configuration is T2G4 EG2 for high spin and T2G6 EG0 for low spin. Whereas in D7, it is T2G5 EG2 for high spin, T2G6 EG1 for low spin. So depending on the nature of the ligand, whether it is strong or weak, a high spin or a low spin complex is formed in metal ions with D4 to D7 configurations, and the electron distribution and hence the CFSE values will also differ accordingly. That is, whether it is a high spin or low spin complex. Now let's see how the electrons are distributed in D8, D9 and D10 metal ion configurations. So with D8, D9 and D10 configurations, there is only one possible way for distributing the electrons between the T2G and EG orbitals. So with D8, we can see that the electron arrangement is the same in high spin and low spin complexes. That is, the configuration is T2G6 EG2 for both high spin and low spin. Similarly, in D9, the electron configuration is T2G6 EG3 for both high spin and low spin. For D10, it is T2G6 EG4 for both high spin and low spin. And the CFSE values will be for D8, it is 1.2 delta O, for D9, 0.6 delta O, and for D10, 0 for both high spin and low spin complexes. So we have to remember that in all the cases, the electronic configuration involving 2 electrons in the same orbital, that is in the case of paired electrons, the actual CFSE value is reduced by the energy spent on pairing the electrons. So in some textbooks, you can see that while calculating the CFSE, they have also mentioned about the pairing energy. That is, if the orbital has one paired electron, then you will be having plus P, where P denote the pairing energy. If there are 2 paired electrons, then plus 2P. Okay. So here we have not mentioned about the pairing energy, but keep in mind that when the electrons are paired up in orbitals, the CFSE value is again reduced by the energy spent on pairing the electrons. In transition metal complexes, the energy difference between the 2 sets of d orbitals is usually small, and the electron can easily be excited from the lower d orbitals to the higher d orbitals by absorption of radiation, particularly in the visible region. And that's why most of the transition metal complexes are colored. So in this video, we have discussed crystal field theory of coordination compounds, how the splitting of d orbitals occurs, and how the electrons are distributed in high spin and low spin complexes.